Hi there, in this video we're going to look at the Laplace transform of the real exponential. So if we write out the Laplace transform f of s is equal to the integral from 0 to infinity, now the function that we're going to use is e to the at, so that's times e to the minus st by dt. Now we can rewrite that as the integral from 0 to infinity of e to the minus, and it would be s minus a of t by dt. Okay, now we've seen from the previous video that the integral of e to the minus st was 1 upon s, so we can quite quickly write out the Laplace transform of this here, and if that sign there just means Laplace transform, so Laplace transform of e to the at is going to equal, well, it was 1 upon s, but now the exponent's been replaced by s minus a, so it's going to be s minus a, and that's going to be exists for all real values of s greater than a. Okay, so that's our Laplace transform. Now what we'll do is we'll have a wee look at that graphically, and we'll see how that looks. So we note that if we draw that Laplace surface, and that's the sigma and j omega, then let's say we choose a value for a equals minus 2, then the Laplace transform would be 1 upon s minus 2. So that would mean that in this instance here, the denominator will give you the poles, so there'll be the 0, sorry, so there'll be a 0 whenever this denominator is equals 0, so that's when s minus a equals 0, there's going to be a pole, so that is when s equals a. Okay, so when s equals a, we're going to get a pole, so let's say a equals minus 2, then we'll have a pole at sigma equals minus 2, which is there, and it's going to exist for the real parts of s greater than a. Okay, so a is minus 2, so for all the values to the right hand side of this pole, the integral will converge. Okay, there will be a Laplace transform, and to the left hand side there won't be a Laplace transform. So let's see how we get this extra bit here on the convergence, so, because previously when we did the previous video, when we looked at just e to the minus st, it only converged for values of sigma greater than 0. Okay, but now it's converging possibly for values of sigma less than 0. So if we were to draw out the Laplace transform, okay, so let's say that's our function there, that's our function f of t equals, I don't know, f of t, it's just a function e to the at, so that's function e to the at. Now what would we do in order to build up the Laplace surface is that we would multiply that by a function e to the sigma t. Okay, so if we pick one particular value, say sigma naught there, so that's a sigma axis, okay, that's our t axis, then that again, that's our t axis there, then we would again have an exponential that look like that. Okay, so it's e to the minus sigma t, I should say. Okay, so the exponential looks like that. When we multiplied both of them together, we have a final exponential that would be our e to the at times e to the minus sigma t, and this function here would then modulate the cos and sine omega t surface, so that would be our cos omega t, that would be minus j sine omega t surfaces. These would be modulated by this function here, and it would produce, and the output here, that would be j omega, that would be sigma, with a function there that would be the imaginary part of one part of the complex plane. Okay, we'll put it in that direction, and the cos omega t would produce the real part of one slice of the complex plane. Okay, so that would be some function that would sit in that axis there. Okay, so let's draw that like that. Okay, so both of these are sitting orthogonal to one another. Okay, and then what we would do is we would then go in and find the magnitude, okay, and that would be our sigma axis there, or j omega axis there, and we would define the value of one particular part of that plane there. Okay, so let's say that point there. Okay, so we find that would be one slice of the complex plane. Now we could build that up by shifting this function and make the value of sigma change, so this function shifts up and down this axis. Okay, so you can imagine this value of sigma, when it gets to 0, you just have e to the 0, which would be 1, and when sigma came back and it was the negative value, then it would be e to the negative, and sigma would be negative, so it would be e to the positive sigma t. So this, at this side of this axis, the function would actually diverge, okay? It wouldn't converge here like this. Now I can show you some of these surfaces just now, so we'll have a wee look at these in MATLAB, okay? So let's look at some of these functions in MATLAB, okay? So let's bring up the original function that we're going to be working with, okay? So this here is the original signal, okay? That's a f of t, that's a function that will equals e to the at, right, that we want to find the Laplace transform of. That there is one particular part of that e to the sigma t surface, okay? So that's sigma naught. So in this instance here it's e to the minus 2t, so when that multiplies that, we get a third function here, which is f of t times e to the minus 2t, okay? So this here is our final function, okay, that we're going to be using to modulate the cos and sine omega t surfaces. So let's have a wee look at the cos and sine omega t surfaces. So that there is the cos omega t surface, which has been modulated by the function for when we've chosen one value of sigma naught, okay? So you can see that there. It's going to be that envelope there is the f of t e to the sigma naught t, okay? And we can again look at the same thing for the sine surface. Okay, that's not that, it's the sine surface, okay? So that's the sine surface, and again we've modulated the sine surface with that e to the f of t times e to the sigma, e to the minus sigma naught t, okay? And that's the sine surface. So of course we create our imaginary real parts of one slice of the Laplace surface by integrating this function with respect to time. So integrate function with respect to time, we get a function of frequency that would run along this axis here, okay? So one other thing to show is the sigma omega sigma e to the sigma naught t surface, okay? So I've actually tried to draw that out here, okay? So you can see that there, okay? Now below 0, negative, we're not interested in, but you could imagine there then that at 0 that would be e to the 0 t, which would just be 1, so that would just be a straight line here, okay? So it'd just be a like a unit step there, okay? But whenever sigma ranged between our minus values and positive values, then we would have an increase in exponential from one side of that the 0 axis, and a decrease in exponential from the other side. So in this side of the axis, this ensures that our function will in fact converge. But if we multiplied it at this side of the axis, then our function would start diverging, okay, because it'd just be getting greater and greater, okay? So that gives an indication there of that surface. So let's go back and just finish this off in smooth draw, okay? So we've seen here just a second ago that this surface here, at this side of it, it would converge, and at the other side of it there would start diverging, okay? So you can see how you get this extra section here of convergence, because if you think about this getting tending towards sigma tending towards 0, as sigma tends towards 0, that thing there would tend towards just the value of 1, but the whole thing would still converge. The whole thing still converge because the function here is still converging. So we could have sigma coming all the way back here, so sigma becoming negative. When sigma becomes negative, this function here starts to diverge, it starts to go up the way as opposed to down the way, but it still wouldn't matter because for a certain area, for certain values here, okay, we would note that this function would still be converging quicker than this one diverges, but you would have a point where sigma would equal that value of a, okay, and when sigma equal that value of a, then we would have a unit step here, okay, right, so we would have a unit step sitting there, and at that point there, the function here would stop stop converging, would start to diverge, and for values beyond sigma, beyond that point there, which is in effect sigma equals a, this whole function here would start diverging, so it would mean that this surface here would diverge, that would diverge, and the whole Laplace transform wouldn't exist. Okay, so that gives an indication there of the how we get this extra factor here in this surface. Okay, so thank you for listening, and I'll get you on the next video. Goodbye.